We're going to talk about the derivatives of the functions e to the x and natural log of x. Now, let me just tell you right at the beginning here that the derivative of e to the x is going to turn out to just be e to the x. And the derivative of natural log of x is 1 over x. So what do these formulas mean and where do they come from? We're going to talk about that in this video. Now, we're going to begin with the function e to the x, but before we can talk about e to the x, I want to talk about what is the difference between the functions y equals x squared and y equals 2 to the x. Well, 2 to the x is an example of what's called an exponential function. Okay, it's not a polynomial. Now, x squared is not an exponential function, it's a polynomial. In fact, it's a quadratic function. So we can notice based on a table of values the difference between these functions. So we've seen the function x squared quite a bit before. Notice that if you plug in, for example, -3, we get 9 as an output, right? -3 squared would be 9. Or if we plug in 5, we get 25 as an output. Well, what about 2 to the x? Okay, if we made a table of values and we wanted to graph the function 2 to the x, how would we do that? Well, notice that 2 to the -3rd power is the same thing as 1 over 2 to the +3rd, which is 1/8. So notice if we plug in -3 in for x here, 2 to the -3rd, we get 1/8 as a result. Now, what about plugging in something like 5? So 2 to the 5th would be 2 times 2 times 2 times 2 times 2, which turns out is 32. So notice the point 5, 32 would be on the graph. Now, 5, 32 would be on the graph of 2 to the x. 5, 25 would be on the graph of x squared. So these are not the same function. Let's go to Desmos. Oh, that's not it. That's my Google search. Let's look at the graphs of these functions. Well, f of x equals x squared, we know what that looks like. That's just a parabola. Now, 2 to the x looks like this. Notice that the order pair 0, 1 is on the graph because 2 to the 0 is 1. We also have 1, 2, 2, 4, 3, 8. Notice as we move to the right, every time we go to the right one, it's doubling in height. In fact, let's look at the height here. If we move from x equals 2 to x equals 3, it's twice as high. Right, as we go back, it's getting half as high every time we move to the left. And that's true not only because I'm picking these whole numbers, 1, 2, and 3, but even if I were to pick a decimal like 1.4, if I were to go from 1.4 to 2.4, the graph would double in height. So every time you move over 1, it gets twice as high. Now the graph of 3 to the x looks like this. Notice that the point 0, 1 is still on the graph because 3 to the 0 power is 1, but instead of 1, 2, it's going to go through 1, 3. Okay, and instead of 2, 4, it's going to go through 2, 9, right? 3 squared is 9. And also, as we move further to the left, instead of -1, 1/2 being on the graph, we have -1, 1/3 on the graph. Okay, now this is 2 to the x looks like this. 10 to the x looks like 10 to the x. We could also graph something like y equals, it would be even steeper. Now, what would e to the x look like? Let's recall that e is a number, right? It's a number that's between 2 and 3. It's 2.718. So we would suspect that the graph of y equals e to the x would be between the graphs of y equals 2 to the x and y equals 3 to the x, and it turns out that it is. Okay, e to the x, and notice it's a little closer to 3 to the x than it is 2 to the x because e is a little closer to 3 than it is to 2. So let me get rid of the other graphs. Now this function y equals e to the x has some very important properties that may not be apparent from just looking at it. In fact, it looks very similar, just 2 to the x or 3 to the x, but it has some properties that the functions 2 to the x and 3 to the x don't have. So the important property we're going to look at is if we look at the slope of the tangent line at any given point. So at 0, 1, it turns out the slope of the tangent line is 1. In fact, if we take any point along the curve and look at its y coordinate, whatever that y coordinate is, that'll also be the slope of the tangent line. So for example, right here at 1.28, 3.59664, the y coordinate is 3.59664. That's how high the point is above the x-axis, but that's also the slope of the tangent line there. The slope there is 3.59. Now, if we were to go over here, notice it's a more gradual slope. Okay, but the slope is actually the y coordinate. So the y coordinate is 0.20598. The slope is also 0.20598. So e to the x has that really interesting property. That's not true about 2 to the x. For example, if you look at the point 0, 1 here, the slope of the tangent line is not 1. It's not exactly 1. In fact, it's a little bit less than 1. If we were to look at 3 to the x, the slope of the tangent line there is a little bigger than 1. But for e to the x, it's exactly equal to 1. So these functions, 2 to the x and 3 to the x, don't have the property that whatever the y-coordinate is, that's what the slope of the tangent line is. E to the x is very unique in that respect. And what that really tells us about e to the x is it is its own derivative. The derivative of e to the x is e to the x. Now, that was not a rigorous proof that the derivative of e to the x is e to the x, but that at least made it plausible. If you wanted to see a rigorous proof, I'm not going to go through this. What we'd have to do is look at the limit definition of derivative. Limit as h approaches 0 of f of x plus h minus f of x over h, and then use the function e to the x. So we'd have e to the x plus h minus e to the x. We'd write e to the x plus h as e to the x times e to the h. We'd factor out at e to the x. The e to the x could come out in front of the limit because we're taking a limit as h approaches 0, so the x is really constant with respect to that. And then you need to know that this limit, you'd have to have some type of argument that this limit here is actually 1. So we're not going to go through a rigorous proof, but you could prove this rigorously if you wanted to. So the derivative of e to the x is e to the x. Now, what about natural log of x? Well, in order to talk about natural log of x, let's first talk about log base 2 of x. Okay, we're going to graph natural log of x, but I think it's maybe a little easier to get started with something like log base 2 of x. So what is the difference between the functions 2 to the x and log base 2 of x? And here's our table of values for 2 to the x. We already looked at this table of values. What is the table of values for log base 2 of x? Well, notice, for example, that log base 2 of 8 is what? Well, 2 to the what power equals 8. Log base 2 of 8 is 3. 2 to the third power equals 8. So notice when we plug in 8 for x, we get 3 as an output. That's actually just the opposite of what happened with 2 to the x. When we plugged in 3, we got 8. In fact, all of these ordered pairs are going to be flipped. 3, 8 is going to be on the graph of 2 to the x. 8, 3 is going to be on the graph of log base 2 of x. In fact, the functions 2 to the x and log base 2 of x are inverses of each other. The x and y coordinates are flipped. What that means in a little more technical sense is that if you do 2 to the log base 2 of x, you get x, and if you do log base 2 of 2 to the x, you get x. And those just come from the properties of logarithms, but this really tells you that if you compose those two functions in either order, you end up getting x. Okay, so these functions are inverses of each other. So what does that mean in terms of their graphs? Well, I've graphed the function y equals 2 to the x here in blue, and y equals log base 2 of x in red. Now, notice these functions are reflections of each other across the line y equals x. Notice, for example, that the order pair 3, 8 is on the graph of 2 to the x, and the order pair 8, 3 is on the graph of log base 2 of x. And notice that these 2 points are reflections of each other across the line y equals x. If you take any ordered pair and you interchange the x and y coordinates, then that new ordered pair will be the reflection of that original ordered pair across the line y equals x. So another example would be, here's the ordered pair 1, 0 on this graph. Well, the ordered pair 0, 1 is on this graph, right? Those are flipped, 0, 1, 1, 0. Notice those 2 points are reflections of each other across the line y equals x. So this is what the graph of y equals log base 2 of x looks like. Now, it turns out that we also have e to the natural log of x equals x, and natural log of e to the x equals x. So what this really tells us is that e to the x and natural log of x are inverses of each other. So what that tells us about their graphs is that their graphs will be reflections of each other across this line y equals x. So here's y equals e to the x. Here is y equals natural log of x. Now, this function y equals natural log of x has a really interesting property that has to do with the slope of the tangent line at any given point. Notice, for example, at the point 5, natural log of 5, so that'd be 5, 1.60944, the slope of the tangent line would be a gradual slope. It's kind of a very gradual slope. In fact, the slope is 1/5. Okay, 1 over 5. If we were to go to, say, 10, 2.300259, what is the slope of the tangent line? Well, it turns out the slope is 1/10. So the slope is always the reciprocal of your input value. So at 8, the slope of the tangent line would be very gradual. It'd be a slope of 1/8. At x equals 1, the slope would be 1 over 1, which is 1. If we looked at a very small value of x, such as 1/10, so 0.1, notice the slope down here would actually be a really steep slope. The slope would be 1 over 0.1, which would actually be 10. So at 0.1 comma whatever the y-coordinate is down here, the slope would be 10. So what this really tells us about the function natural log of x is that the derivative of natural log of x is 1 over x. So that gives us our other formula here. The derivative of natural log of x is 1 over x. Now, again, this was not a rigorous proof. If we wanted to prove this rigorously, we'd have to use the definition of derivative. And our function f in this case would be natural log of x. So we'd have natural log of x plus h minus natural log in the numerator. For example, natural log of x plus h minus natural log of x would be natural log of x plus h over x. That's the quotient property of logarithms. Then you'd have to rewrite this part on the inside. X plus h over x is just x over x plus h over x. X over x is just 1. Then you'd have to do a little bit of trickery. You'd have to do something called a change of variables. Again, we're not going to get into it much. The x you'd ultimately have to use the definition with respect to the number limit. So you'd pull it out, alternative definition of the number e. But it would turn out that you could prove rigorously that the derivative of natural log of x is 1 over x. But instead of proving them rigorously, we've given some plausible reasoning about why these seem like they could be true. Okay, and it turns out the derivative of e to the x is e to the x, and the derivative of natural log of x is 1 over x. So we're going to use these two formulas.